In this video we'll be studying some mechanical properties of metals, and we'll be also discussing the elastic and plastic deformation. So mechanical tests, in this you can see four figures, one of tension, compression, shear, and the other of torsion. So first of all, you see that the initial dimensions of the specimen are in the non-continuous line, the dashed lines you can see over here, and the final deformed dimensions are with the continuous lines and the solid shapes. Okay, so what happens in tension, that two opposite forces are applied and a stretch is being made. So what happens is the length of the specimen is increased, as you can see, and the diameter of the specimen is reduced. But in compression the reverse is occurring. Two forces are applied and towards each other, and the diameter is increased and the length is reduced over here. But you can see that the overall volume of the specimen remains the same. In shear, what happens is two forces are applied in opposite direction on a parallel cross section, as you can see with the area A naught, similar with these two directions. And in torsion, the two forces, as you see over here, acts as to produce a twisting effect. So that is basically torsion. Okay, so in tension tests, this is a figure of the UTM machine, that is ultimate tensile testing machine, in which there is a load cell which will apply the load, the force. Here you can grip the specimen. These are two grips, and this is an extensiometer which would basically measure the extension, the increase in the length during the tensile load. Okay, so this is a specimen. Usually this is called a dog bone specimen, but it can also be a straight specimen. It depends on case to case. So when we'll apply a force on this specimen's area, a stress is generated. That is called the engineering stress. So basically that stress is the ratio of force and cross-sectional area, and with that stress a strain is also produced. So the strain is the ratio of change in length upon the original length. The change in length can be calculated as the increased length and the original length. The increased length in case of the tension test would be greater than that of the original length, but in case of compression it would be less than that of the original length, because the diameter because the length would be reduced and the diameter would increase in compression. Okay, so in a tension test we get this line when we put the stresses and strain on a graph. So basically we have these certain points. At point A, this is the proportion limit or the elastic limit. B and C are the yield points, the upper yield point, the lower yield point. D is the ultimate stress point, and E is the rupture point or the fracture point, which we'll be discussing in the later slides step by step. Okay, so what is shear stress and strain? Basically shear stress is again the parallel forces which are unlike parallel forces are the shear forces, and this area is the cross section area where the forces are applied. So the shear stress is the force upon area, and the shear strain now, so this is gamma equals to tan theta. We can also find it through that, but let's discuss that what is the difference between the normal strain and the shear strain. So in the normal strain you can see that if you applied the load in the x direction, the change in length in the x direction upon the original x length would be your strain. And if you apply the load in the y direction, the change in length in the y upon the original y length would be your strain in the y direction. But in case of the shear strain, what happens is, if you apply the load in the x direction, this increased length from the original is your delta x, and you can see that this length of the perpendicular, the y, is also changing, it's increasing. So we have to consider this as well. So if you are applying the load in x direction, the shear stress, the shear strain would be delta x upon y. And you can if you study the geometry of this, you can also calculate or write it down, the shear strain in xy direction, that would be equals to tangent of this angle, that is alpha x. Similarly, if you apply the force in y direction, your strain would be this is usually gamma, not epsilon. Epsilon is used for normal strain or engineering strain, but gamma is used for shear strain. So gamma yx would be delta y upon x, or you can also write it as let's do it gamma y x equals to tangent of angle alpha y. Alright, so like this we can calculate the shear strain. Okay, so the standards which are used for a tensile test or a compression test or a shear stress are E8 and E8M for tensile testing, ASTM E9 for compression testing, ASTM standard E143 for shear modulus, for determining shear modulus on room temperatures. We sometimes we also use some British standards. This standard is American standard, but sometimes we use standards such as ASM, British standards, and Japanese standards as well. But this is the most common standards which is used for mechanical testings. So elastic deformation. What is basically elastic deformation? I'll give you an example of a rubber band. So if you have a rubber band of this length, let's suppose of 3 centimeters, so you stretch it out till 5 centimeters, and then you unstretch it, so it comes back to its original position of 3 centimeters again. So this is, in this case, your deformation is elastic, because there is no strain. All the strain is recovered. The strain would be 2 centimeters here from this side to this side, as this is of 3 centimeters. So all this strain is recovered in the final stage. So this case would be of elastic deformation. Okay, and you can see that this stress is proportional to the strain, with E as the proportionality constant, and this E is the modulus of elasticity, or simply we call it elastic modulus or Young's modulus, which is the stress upon the strain. Okay, so this is basically elastic deformation. So what happens when we deform anything, any material or specimen in the elastic range, is when we apply a load. Okay, when we stretch it, so what happens is the interatomic spacing is being increased, and interatomic bonds are being stretched, and the forces is being compromised now. But if we release it, it comes back to its original position. only if it is in the elastic region. If we stretch it beyond its elastic limit, the material would have a permanent deformation that we'll be discussing later on. So here is a comparison of Young's modulus with temperatures. You can see that when we increase the temperature, the modulus of elasticity is reduced. Why? Because the kinetic energy is increased, and it does not the material does not resist the deformation anymore. So the modulus of elasticity is compromised while increasing the temperature. Next we have shear modulus, and this is also called the modulus of rigidity. So it is represented by G, and again it is the ratio of the shear stress upon the shear strain. Alright, so now we have Poisson's ratio. Poisson's ratio is basically used in engineering applications to analyze the stress and the deflection properties of materials like plastics and metals. We have to get an idea that how much a material would deflect if we apply such and such certain amount of stress or a certain amount of load on that. Okay, so basically that is the ratio of the transverse strain upon the longitudinal strains, or we can say it as a lateral strain upon the longitudinal strain. Alright, and if we want to get a relationship between the elastic modulus and the shear modulus, because in an engineering application both all the stresses are occurring at the same time. So to get a relation between elastic and elastic modulus and modulus of rigidity, this is the relation E is equals to 2G into 1 plus the Poisson's ratio. So here are certain properties of different metals at room temperature of modulus of elasticity and shear modulus, and also of Poisson's ratio. So you can see over here that the modulus of elasticity is 207 for steel and 407 for tungsten. So it's very high. That means that it would resist this amount of stress while in the elastic region. So this is a lot of stress which tungsten and steel are resisting. And the shear modulus is also high. You can see that 83 for steel and 143 gigapascals for tungsten. So here we have an example problem which I'll be discussing. Let's read it. A tensile stress is to be applied along the long axis of a cylindrical brass rod that has a diameter of 10 millimeters. Okay, so this you can see this dashed figure, the dashed surface, with the non-continuous lines initially had the diameter of 10 millimeters. Okay, determine the magnitude of the load required to produce 2.5 into 10 power minus 3 millimeters, that is 2.5 micrometers in diameter if the deformation is entirely elastic. So we know that the deformation is in the elastic region, so we can use the modulus of elasticity, and the final diameter of the surfaces of the specimen is given as 2.5 micrometers. So if you're not given the elastics modulus or the Poisson's ratio, we can find it for brass in the table. You can see that for brass the modulus elasticity is 97 and the Poisson's ratio is 0.34. So here is the solution. I have put the solution for you guys, but I also want you to do it on your own. So let's start. So when the force is applied, the specimen will elongate in the z direction. That is, when the force is applied, you can see over here the elongation is in this direction, the z direction, and this is the x direction, xy direction. Okay, and at the same time experiences a reduction in diameter. So there is an increase of length, simultaneously there is a decrease in the diameter as well. So the x and y quantities would be same because it's a circular part. The x and y both would be the radius. So the initial diameter was 10 and it would reduce to 2.5 micrometers. So let's find the strain in the x direction, that is the original diameter is 10 millimeters and the change in diameter is 2.5 into micrometers. And why there is a negative sign? Because the diameter is reduced. The initial diameter, pardon me, the diameter is reduced now, so the final diameter you can see that is reduced and the initial diameter was much larger, so there would be a minus sign over here. Alright, so now we studied that the Poisson's ratio was the lateral strain upon the longitudinal strain, in this case omega epsilon x upon epsilon z. So we'll rearrange the equation and we'll put the Poisson's ratio over here. We'll put the negative sign as well, so then the negative cancels, and we'll divide these values to get is 7.35 in power minus 4. Again, this is a dimensionless quantity, and because this is a dimensionless quantity, because both the dimensions, millimeters and millimeters, would cancel out. So we get this longitudinal strain over here. So now we can calculate the stress basically. So we know that the stress is equal to the strain into the elastic modulus. So we'll multiply this value and the modulus velocity, which we got it from the chart from the previous slide, and we get this value. This would be in megapascals because the elastic modulus is in megapascals and the strain is dimensionless. Alright, so once we have the stress, we can easily find out the force. We know that the stress is equals to force divided by the area. So we'll multiply the area with this stress and to get the force. So for the area, what we'll do is we'll take the initial cross-sectional area. The diameter was given as 10 micrometers, so we'll take this, 10 millimeters, so we'll take this. We'll also add this 10 power minus 3 so that we can take our dimensions in meters. And why have we divided by 2? Because that was the radius which was given, and to convert the radius into diameter, we divide the diameter by 2. So we'll multiply it and we'll again multiply it by pi, because we know the formula of area is for a circle, it is pi d upon 2 square. So we have taken this area, this is our stress which we got it previously. Again we'll take 10 power 6 for mega, so we have to keep all our units in the SI units, and we'll multiply it and we'll get this answer of 5.6 kilonewtons, or we can say 5600 newtons. So this was the solution. Okay, moving forward, up till now we have discussed till the elastic limit. So after that, if we stretch our specimen, there would be some plastic deformations. I'll give you an example again, the same of the rubber band, that if you have the rubber band of 3 centimeter initially, you stretch it to 6 centimeters, and it comes back to 3.5 centimeters. But there is a strain recovery of 2.5 centimeters. So this 0.5 increase in the dimension is now the plastic deformation. Okay, so you can see over here that once the elastic limit ends, that is the yield point, and this is also the yield stress at which the material would be starting to deform permanently. So we have two cases. In one case, we can see on the right, we can see that two upper and lower yield points are clearly in the figure, but in the left one there is no clear yield point defined. So both of the graphs are correct, but are of the separate cases. So in the right one, first we can see the upper yield point. This is the situation where the load starts reducing and the strain is increasing. So the load would just for a little while it would reduce, and till the lower yield point, when the load is stagnant but the strain is drastically increased, and after that it would uniformly, the load and the strain would uniformly increase. But again, it is not linear. But in this case, where the yield point is not clearly mentioned or not clearly defined, so what we'll do is we'll take a offset of 0.2% of strain, and we'll draw a line parallel to the our proportional limit until it meets our line. So this would be our expected yield point. Okay, so here is another example of the stress strain curve, a more explained much clearly. So what is happening over here, we can see that this is elastic deformation, and up till this the deformation was elastic, and after this is the yield point or the yield strength, and after that stress, the deformations would be permanent. Okay, so what is happening in the elastic region, that this is our specimen, and if we apply the load, the length is increasing over here, but it would come back to its original position when the load is reduced or it is unloaded. Okay, so but when we increase the load in a tensile test, or when we increase the stress, what is happening, that there is a permanent deformation going on. So the strain now would be permanently retained in the specimen. Alright, so up till this stress, the highest the specimen can bear, the permanent deformations would be retained, and after that what happens is necking. Necking is the reduction of diameter, as you can see over here, through a localized region. That this is on this localized region, the diameter is being reduced, and if we increase more stress, or if we increase the load at a certain point, the specimen is now fractured. Okay, so why the graph is going down over here, because why the stress is being reduced, because of this necking, since now the area is very, this area where the load is being applied is very small. So at a very very small stress, it can create a larger strain, as you can see over here. Okay, and ultimately the specimen would fracture. So this region would be called as the uniform plastic region, as since the plastic deformation is uniform. And after necking, since it can be over here, it can be over here, it can be over here, it can be at any localized region, which you can also visualize in a tensile test. So after necking, once the necking starts, the plastic deformation is non-uniform. Here is another figure which you can in which you can see that up till this there is some permanent deformation, but there is no necking. But after the highest stress, that is the tensile strength or the ultimate tensile strength of the material, after which it would start necking, and the diameter at a localized region in the specimen would reduce, and ultimately it would fracture. So ductility. What is ductility? Basically, it is defined as the degree to which the material resists or sustains plastic deformation under the tensile stress or tensile or in tension. Okay, so you can see that in this figure, this is very highly ductile, that it continues to reduce its area, and it would also continue to elongate before fracture. Okay, so it's a very highly ductile material, and this is somewhat a less ductile material. You can see that there is some necking. There is, because the material would go on stretching up till its maximum limit, and then ultimately it would break down. So this is a less ductile material, and then there is a brittle fracture. So in the brittle fracture, there would be no ductility. There would be very less permanent strain, and immediately after its elastic limit, as you can also see in this blue line, that immediately after its elastic limit, on a very small stress compared to this, it fractures. It does not tend to deform, but it suddenly fractures. So these kind of failures are very catastrophic, that if a brittle fracture, if the material is brittle, it would not allow you to, it would not indicate that a fracture is being, or it would happen in future. But in the ductile material, it would neck out, and you can indicate that the fracture has been occurred, so you can easily replace the specimen. So you can see over here that a ductile material is retaining permanent deformation throughout the stress. Alright, by retaining of permanent deformation, I mean the retaining of strain. So how can we quantify the ductility? So we can quantify it in two types, that is percentage elongation and reduction in area. So in percentage elongation, we can quantify the ductility as the length increased upon the original length, and the reduction of area, we can quantify as the area reduced as per the original area. So these are two ways to quantify ductility. One more important thing, that is ductility and malleability. So in ductility, what happens is, you would have studied a definition of ductility in your earlier classes, that it is a ductile material can form wires, and it is used for wire making. But as material scientists and studying a material science course, we should know that ductility is the degree to which the plastic deformation is retained under tensile stress. Okay, so in ductility, there is tensile stress of importance, and but in malleability, the compression stress is of importance. Okay, so this is the ability of a material to sustain plastic deformation under compression or a compressive load. So you have studied that malleability is ability of materials to make to be drawn into sheets. So while sheet making, what we do is we just, that like in this figure, that we are hammering it out. Okay, so by hammering we are applying compressive stress, and then the size of this metal is increased to a sheet. So in this, tensile strength and ductility relationship versus with temperatures. So this figure shows you the tensile engineering stress strain curves of AISI 4340 steel at different temperatures. Okay, so in this figure we can see that while increasing the temperature, the ductility is being increased, but there is a compromise of strength over here. We can see that the ultimate tensile strength of this at the specimen at 180 degrees is very high, but of this is very low, the specimen at temperature 500 degrees centigrade. Okay, so while increasing the temperature, we can see that we can observe that the ductility is increased, but the strength is being compromised. The ultimate tensile strength, or the tensile strength, is being compromised, and it is lowered. So now resilience. Basically, what is resilience? Resilience is the energy that is absorbed during the elastic deformation, or only in the elastic region. Okay, so it is the capacity of a material to absorb energy, again, when it is deformed elastically, and then upon unloading to have this energy recovered. So whatever energy recovered in the elastic region is the modulus of resilience. So how can we quantify the modulus of resilience? Is by is 1 upon 2 stress into the strain, and we can also write in terms of the elastic modulus as the square of stress upon 2 into the elastic modulus, or modulus of elasticity. The units for modulus of resilience would be joules per meter cube, as this is the energy absorbed per unit volume. Okay, so what is toughness now? Toughness, as you can see from this image, that when we strike a hammer on this thin plate, it can be a plate or it can be a wire, this wire or the plate is trying to bend, it is not breaking out. But if the material is brittle, it would immediately break out into 2 or more pieces. So that means that this is brittle and this is tough, that it can absorb more energy. So how can we quantify this? It is the measure of the energy absorbed up to the fracture points. So whatever energy is absorbed in the plastic region and in the elastic region, both would be called as toughness. So what we'll do is we'll just integrate this area to find out the toughness. Here you can see that which I was discussing in the temperature and ductility graph, that when the ductility is increased, as you can see over here with temperatures, so the strength is being compromised, and again there would be less toughness because there is less area over here. But at optimum ductility, we can get a higher strength and we can get a good toughness. But if we lower the ductility, we can get a very high strength, but for a very less but with a very less strain. Okay, so again, for a very high strength, the ductility would be very low, and again it would also have a very low toughness. So elastic recovery after plastic deformation. Again, I'll be using that example of a rubber band, which I used previously. So let's suppose if you have a rubber band, I'll change the color first. Let's take it to this color. Okay, I have a rubber band of 3 centimeters, and I stretch it to 6 centimeters, and then I unstretch it, so it comes to 3.5 centimeters. So there is a strain of 0.5 centimeters that is permanent, but the other strain, which is this, is of 2.5 centimeters. So this strain which was recovered is elastic strain, because this is not permanent, so this is the elastic strain, and this 0.5 would be the plastic strain. Okay, so this would be the elastic recovery of strain. So from this figure, how can we study it? That for example, this is the elastic region, and this is the plastic region, and the plastic stress we are applying around it. So when we unload it, okay, so the graph comes back to this position, rather than it should have gone through this line. Sorry, I'll erase it. It should have okay. So when we unload it, it should have come to this line rather than this line, but it eventually comes to this line. Why? Because the strain value should be this one. For example, it should be 5, but it comes back to 3 again, 3.5. So this recovery is the elastic recovery, as I explained you with the example of this rubber band. Alright, so that were the mechanical properties and the elastic and plastic deformation which we studied earlier. So now, what is hardness? So hardness cannot be defined as the mechanical property. Basically, hardenability can be defined as the mechanical property, but not hardness. So what is hardness? That hardness is a measure of material's resistance to localized plastic deformation. What is meant by localized? That is on a certain point. For example, you have metal specimen like this, and you just check hardness on this point, on this point, on this point, on this point, and on this point. So these are localized point when you can check the hardness. So why do we frequently use hardness testers and hardness testing? Because they are very simple to operate and very inexpensive, not as expensive as tensile testing and impact tests. So also the apparatus is very simple to use. The other thing is that the test is not destructive. It is non-destructive. Now you would say that we are putting some indents, so it should be destructive, but it is not in real. Why? Because the area of the indents is very, very low. It's in millimeters, it's in micrometers, or sometime it is in nanometers. So it is a very small localized region that does not affect the overall property of the specimen. So the test is non-destructive. All right, and through this test we can also predict some other mechanical properties like tensile strength, impact energy, or through some computations we can also find out the fracture toughness of a material. So there are three types of hardness tests which are very common. That is, one is brittle hardness test, one is Wicker hardness test, and the other is the Rockwell hardness test. In the other slide you can also see that there is a Knoop micro hardness, which is basically a micro Wicker hardness test with a very low load. So what we do is we have certain indenters. So in Brittle hardness tester we have a 10 millimeter sphere of a steel or a tungsten carbide ball. Okay, so it's a ball, or we can call it a sphere of tungsten carbide or steel. In micro hardness we have a diamond pyramid shaped indenter, and in a Knoop hardness we also have a diamond indenter shaper with some different dimensions, because the indent would be on a very lower load, on a very lower force, you can say. And in Rockwell and superficial Rockwell, you have basically a diamond indenter which is in a cone shaped, and the superficial Rockwell we have also the steel spheres with different diameters. Okay, so for a higher load we use this diamond cone, but for a low loads like 10 kg, 15 kg, 30, 45 kg, we use these spheres. So what we do is this is a hardness tester. What we do is we place our specimen on this anvil. Sometimes the hardness testers are also incorporated with the microscope, but not necessarily. And then we perform an indent, and the machine gives us a value of the hardness. So the units of hardness, the hardness values which will be in HB for Brittle test, HV for Vickers, HK for Knoop, and HRA, HRB, and HRC for Rockwell tests. So Liberty shapes and the failure. So you might know that Liberty shapes, that these were supplied by USA to Britain in order to help them to win the World War against the Nazi Germany. So what they did is they mass produced these ships, these Liberty ships, ignoring some material selection and design parameters to design a ship, and the ultimate goal was to provide maximum number of ships. So they didn't much thought about the design parameters and the mechanical properties. So what happened was the material for ships which was used, and the properties of that material were expected at room temperature, but the ships were supposed to be used in a sub-zero temperature or a very lower temperature. That was not actually the room temperature, about 25 to 30 degrees centigrade. So in that case, the ships were failed, and one of the other reason was these ships were welded rather than riveted. So because the design parameters of these ships required riveting, but they used welding rather, so that they can mass produce the ships in a very small amount of time. So the ships previously, which were produced in 6 months, now they were produced in 3 to 4 weeks. So that kind of time span they had to reduce, keeping the consequences of the war. So why it is of importance, why do we study it in materials sciences? Because we expect this ductile to brittle transition. So what happened with the Liberty ships, that the design and selection of materials was made at room temperature, but when they were in service, when they were put to the ocean, it had a very lower temperature, or a sub-zero temperature, because you know that the area near Europe, the European areas are very cold. So the temperature of the ocean, the sea, was also sub-zero, that was around 0 or lower. So what happened was the material which was supposed to fracture in a ductile manner at a very high impact energy was now failed at a brittle fracture at a very lower temperature. You can see over here. So let's study what is impact energy. Impact energy is basically when you strike a material against some standard testing specimen and it breaks. So that impact, basically the energy absorbed during the impact is basically the energy, the impact energy. Okay, so what happened with the Liberty ships, that uh, the material which they used had a very high impact energy at room temperature. Suppose this is the room temperature. And they expected this ductile fracture at a very high impact energy. But what happened, that they sent the ships into a very lower temperature, that was around 0 or sub-zero, lower than that. Okay, at this temperature. So immediately what happened, that the body of the ships started to crack. Okay, so that failed the Liberty ships, and some of the ships which were made in a time of 3 weeks or 4 weeks were immediately cracked when they were sent into the ocean. Okay, so what do we learn from this is the ductile to brittle transition, in which this is the transition temperature. This is basically the temperature in which the ductile the impact energy is reduced, but we should have a higher range of this temperature, because if this temperature would high, we can easily the body can resist some of the impact energy rather than fail it in a brittle manner. So what are the factors affecting to ductile to brittle transition? One is the carbon content. So if we take the ferrous alloys or the iron alloys, especially steels, so when we increase the carbon content, you can see that we get a variety of, wide range of transition temperatures, as in this case, in this case again, similarly in this case. And when we reduce the carbon content, you can see that there is very less range of transition temperature. So the material would not give us the indication, but would immediately a ductile material would immediately fail in a brittle manner when the transition temperature is achieved to the brittle fracture point. Okay, so when we increase the carbon content, what happens is that we get a wide range of temperature, so we can predict that our specimen or our material would fail, or it would provide us some indications rather than to fail in a catastrophic manner. So this is one of the factors, the carbon content in ferrous alloys. The other is crystal structure. This crystal structure we'll be discussing in the later lectures. So if we have a FCC or HCP, if we have a face-centered cubic or a hexagonal closed packing structure of any metal, there would not be any transition from ductile to brittle, because due to their crystal lattice arrangements. And if we have a low strength steel which has a BCC structure, or any other material which has a BCC structure, so it would have some ductile to brittle transition. So what is desired is to get a wide range of this temperature rather than a very steep line like this, which we saw in this case. Okay, so again, high strength materials do not matter this ductile to brittle transition. The third factor that affects the ductile to brittle transition is the grain size. So if we have a small grain size, we can get a wide range of transition temperature, or a service temperature we can call it. You can see that in this small grains, what are basically grains, that if you analyze a metal part in a microscope, you'll see certain grains. So what happens is, if the grain size is very small, we can call it fine grains, or we can call it refined grains. Okay, so in that case we get a wide range of surface temperature, we get a wide range of transition temperatures. The material does not fail immediately in a brittle manner, but rather it gives us such indications. Okay, so you can see that when the size increased, the range of temperature is now decreased, and in this case, large scale, the large grain size structures have a very small range of temperatures which we can take into account. So that's all for the this lecture. Thank you.